Welcome back. Let's learn about curvature of space curves. Alright, so at the most basic level, we define curvature as the measure of how sharply a curve bends, or another way to think of it is that curvature is a measurement of a curve's failure to be a line. And that should make sense because a line is straight, right? And so any deviation from being a straight line means that a curve would have some amount of curvature. And we represent the measure of curvature with the letter K. Now, sometimes you will see a Greek letter known as kappa, which looks very similar to a K. You'll see that used for curvature. But for this video and all of my other Calc 3 videos, I will represent curvature with the capital letter K. Alright, now to get a better idea of what we mean by curvature visually, if you take a look at this plane curve I have right here, we can see visually that at point A, the curve bends more or curves more sharply around that point than the curve does at point B, right? You can see that the curve is a little bit more straight around point B compared to point A. So we would say that the curvature on this plane curve is greater at point A than point B. There is more curvature or more bend to the curve at that point compared to point B. And we could say the same thing when looking at point C and comparing that to both points B and A. The curve bends more sharply around point C than it does at point B or point A. So we would say that the curvature at point C on the plane curve is greater than the curvature at points B or A. Alright, so that's how you can sort of get an idea of curvature visually on a curve, but mathematically, we think of curvature as a comparison between the change in the tangent vector and the arc length of the curve. So for example, if we take a closer look at each of these points on the plane curve, specifically the areas around those curves, right? We're not just looking at the points themselves, but what's going on with the curve around those points. Starting with point A, if you were to look at tangent lines to points around the area of that point, they would look something like this. One tangent line might look like this, then another would look like this, and then one might look like this. You can see that there are some noticeable changes in the slope of those tangent lines as you move along the curve. So there is some change in the tangents compared to the arc length. Now if we do the same thing for the area around point B, here's what some of the tangent lines would look like. You'd have one like this, and then another one like this, and then let's draw one more over here like that. You can see with these tangent lines that there are minimal changes in their slope, right? These tangent lines are not all the same, they are different, but the difference is minimal compared to the changes we saw in the slope of the tangent lines around point A, right? There are some noticeable visual changes in the slope of those tangent lines, not so much around point B. And so as we walk along the curve, the changes in those tangents compared to the arc length are minimal. And then if we do the same thing for this section of the curve around point C, and by the way, all three of these little sections come right from this curve over here. We're just magnifying each of those points and a section of the curve around them. But if we were to draw some more tangents around this point C on the curve, one might look like this, another one might look like this, another one might look like this, and another one might look like this. You can see that there are big changes in the tangents this time around, right? Each of these tangent lines has a significantly different slope than the previous one. There are big changes in the tangent compared to the arc length. As you walk along the curve, the tangent lines are not just noticeably changing, they have pretty big changes. Alright, so in each case, as we walk the curve, the measurement of curvature will be bigger or larger if the tangent does not change too much, then the curvature would be less, like you see around point B. The tangent lines barely change around point B compared to point A or point C, so the curvature is clearly less around that point compared to those other 2 points. Alright, so as I've said earlier, mathematically, we define curvature as how the tangent is changing with respect to the arc length. And so we can represent that with the following formula. The definition of curvature is this. For a smooth curve given by the vector function r of s, where s is the arc length parameter, the curvature at a specific value of s is represented by this formula. The curvature k is equal to the magnitude of dt ds, or the change in the tangent with respect to the change in the arc length. All right, or another way that you could write that is the magnitude of the vector capital T prime of s, the derivative of the unit tangent vector in terms of the arc length parameter, right? Remember that that notation of the vector capital T represents the unit tangent vector. We looked at this notation and how to find unit tangent vectors in a previous lesson. A unit tangent vector is just the derivative of a vector function that is then divided by its magnitude such that the magnitude is then 1, so that you would have a unit tangent vector. Okay, and speaking of a magnitude of 1, if you remember back to the previous lesson on the arc length parameter, we said that the derivative of a vector function in terms of the arc length parameter, that derivative r prime of s, would be a unit tangent vector, right? The magnitude would be 1. So because of that, since the magnitude of r prime of s is equal to 1, that means that r prime of s would be the unit tangent vector t of s, and so the derivative of that would also be the second derivative of the vector function in terms of s. All right, if you take the derivative of r prime of s, you get r double prime of s, and since that would be the unit tangent vector in terms of s, that means that r double prime of s would be equal to t prime of s. So there's actually another way that we could write out this definition of curvature. You could say that the curvature k is also equal to the magnitude of r double prime of s, the second derivative of the vector function with respect to the arc length parameter. Okay, so if you need a refresher on the arc length parameter and why this is true, feel free to go back to that lesson where I show you why this is the case. But we can use that fact to rewrite the definition of curvature a slightly different way, okay? Now remember, the bottom line here is this. Curvature, mathematically, we think of curvature as a measure of how the tangent is changing with respect to the arc length. That is why we have dt ds. dt represents the change in the tangent, and ds represents the change in the arc length because s is the arc length parameter. Okay, and as you can see here, since t is a vector, we could also represent dt ds with a vector. It is t prime of s, and we are taking the magnitude of that vector because curvature is a scalar value, right? We want a specific number for the curvature. We're not interested in a vector, all right? We want to know a specific value for curvature at a point along a curve. And by the way, a couple notes about curvature here. If the curvature k is equal to 0 at a particular point or for the entire curve, then that means that the curve is a line, okay? If a curve has 0 curvature, then it's not curving at all, so it has to be a straight line, okay? And then in the context of calculus 3, we think of curvature as a non-negative scalar quantity, so it does not consider the direction of a bend, just the magnitude. All right, so in other words, what that means is that the curvature k should never be negative within the context of calculus 3. K will always be greater than or equal to 0. We just want to know the magnitude or the amount of curvature for a curve. We're not really interested in the direction or which way a curve is bending. There is a way to measure sine curvature or to see which way a curve is bending, but that's something that you are more likely to encounter in a future physics or engineering course. All right, so in the context of calculus 3, curvature will always be positive. But now if we go back to our definition of curvature, you might have noticed, in fact it's very obvious, that we are working in terms of the arc length parameter s. All right, and if you think back to our previous lesson on the arc length parameter, you might recall that reparameterizing a vector function to be in terms of the arc length parameter s was not exactly a quick and easy process, right? There's a lot of steps involved with reparameterizing a curve in terms of its arc length. So most of the time, when we calculate curvature, we're probably not going to want to do that unless we are given a vector function in terms of that arc length parameter. Okay, if you were given a vector function in terms of some other parameter that is not the arc length parameter, such as t, then this definition or this formula is not all that helpful. You can do it, but it's probably going to require a ton of work that we can avoid. Because thankfully, there is another way to calculate curvature. And so let's take a closer look at this definition and find this other method. And what I'm going to do to start is rewrite the unit tangent vector in terms of the arc length parameter, right? The function that we are taking the derivative of here. Instead of writing it as vector t of s, like this, I'm going to change it so that we represent the arc length parameter with s of t, the arc length function, right? Because that's really where s comes from. If you remember back to the previous lesson on arc length parameterization, that arc length parameter s would be in terms of the other parameter t, and so we could rewrite s as s of t. So I'm going to do that here. We'll have the vector function t of s of t. All right, so that's a vector function with an inside function that is a regular function. All right, s of t is not a vector function. It is what we would call a real valued function, or a function that you were used to working with in the past. Okay, and so then if we were to take the derivative of this vector function, technically we would be taking the derivative with respect to t, because that inside function is defined in terms of t. And also, when we take the derivative here, we will essentially be using the chain rule. We'll take the derivative of the vector function on the outside, keeping the same inside function, and then multiplying by the derivative of that inside function. We get that from one of the properties of the derivative of vector functions. All right, so if we take the derivative, it will look like this. I'm going to write it using this notation, but remember we are taking a derivative now with respect to t. We would write it like this. You'd have d capital T, or vector capital T, divided by dt, and that would be equal to the derivative of the vector function, keeping the same inside function. So you'd have t prime of s of t, just like that, and then you would multiply by the derivative of the inside function. So you would multiply by s prime of t. Now, rewriting these derivatives in this same notation, here's what we'll get. D capital T dt is equal to the derivative of the unit tangent with respect to the arc length function. We can rewrite that as dt ds. So we have dt over ds, and then that would be multiplied by the derivative of s with respect to t. So we'd have ds dt. Okay, so that's just a result of the chain rule here, and you can see that this would be true because if you canceled out these ds's, you'd be left with the same thing on both sides of the equation, d capital T dt. All right, but now the reason I did this is because we can then solve for dt ds, the vector that we take the magnitude of to get the curvature. All right, so if we solve for that, here's what we get. You would be dividing both sides by ds dt, so you would get that dt ds is equal to dt divided by ds dt. Okay, once again, I just solved for this right here by dividing both sides by ds dt. And so this is what we get. And then here's what we can do. We know that dt would just be the derivative of the unit tangent vector with respect to t. So you could rewrite that like this. You'd have capital T prime of t. That's what we have in the numerator there, the derivative of the unit tangent vector with respect to t. But what about the denominator? What is that? What is ds dt? Well, thinking about it logically, ds dt would be the derivative of the arc length parameter s with respect to t, so you could write it as s prime of t, but that's not going to be all too helpful here. We don't want to have to use the arc length parameter at all. We're trying to find another way to calculate curvature that doesn't involve the arc length parameter. And so instead, here's what we can do. Remember what the arc length function is equal to. This is once again from the previous lesson on arc length parameterization. We know that s of t is equal to the integral from some lower bound a to an upper bound of t of the magnitude of the derivative of our vector function. All right, or if you remember, we write it in terms of u for the integral. We write r prime of u and integrate with respect to u. And so that's what s of t is equal to. And so if we take the derivative of that, if we take the derivative of both sides of this equation or of both sides of this formula, watch what happens. And specifically, we are going to take the derivative with respect to t. We would have the derivative with respect to t of s of t is equal to this integral that we will also take the derivative of with respect to t. So that looks like this, d dt of that entire integral. And as a result of that, we find that ds dt is equal to just the magnitude of the derivative of the vector function evaluated at t, right? It's just going to be equal to this. We get that using the fundamental theorem of calculus. That's sort of what we're invoking here with this derivative of an integral. If you remember back to calculus 1, differentiation and integration are just opposite operations. So if you integrate something and then evaluate it at the bounds of integration, so it will be in terms of t, if you then take the derivative of that integral, you get back to the original thing that you integrated, but it will then be in terms of that variable t. Okay, so the derivative and the integral cancel each other out, so you're just left with the magnitude of r prime of t. So that's what ds dt would be equal to. It's just the magnitude of the derivative of the vector function. So that's what we can put right into this formula. We'll have the magnitude of r prime of t. And now if you look at what we have here, everything is in terms of t. We're almost there. We've almost found a formula to calculate curvature that doesn't involve the arc length parameter. The only thing we're missing here is the fact that curvature is not just equal to dt ds, it's equal to the magnitude of dt ds. So you would want to take the magnitude of both of these vectors. We already have the magnitude of r prime of t right here, but we would also need to take the magnitude of t prime of t. All right, so to finalize this formula, k would be equal to the magnitude of that derivative. And so we take the magnitude of the numerator and denominator, which results in this formula right here. The magnitude of the derivative of the unit tangent vector with respect to t divided by the magnitude of the derivative of the original vector function. Okay, so this is the formula you are going to want to know for finding curvature of space curves. This allows you to find the curvature without ever needing to reparameterize your curve in terms of the arc length parameter. You can work entirely in terms of t. All right, so this is the formula that you will use most often. However, as a result of this formula, there is actually another way to calculate curvature in terms of t, and this method or this formula is particularly helpful when working with polynomial expressions in your vector functions. So when your vector function has components that involve terms like t squared or t cubed, nothing like a trig function or exponential function, just simple algebraic expressions. When you have that, there is another formula that is helpful. It looks like this. The curvature k is equal to the magnitude of the cross product between the first and second derivatives of your vector function. So that looks like this. You'll have r prime of t cross r double prime of t, and then that's divided by the magnitude of r prime of t cubed. Okay, now this formula is found by rewriting the magnitude of the derivative of the unit tangent vector. I'm not going to show you the proof here, as it's somewhat lengthy and ultimately not necessary for you to see in order to use the formula. And also, this formula is not used all that frequently. You will use it from time to time, but it's not the main formula. So I'm not going to take the time in this video to show you the proof. However, I will have a video showing you how to get to this formula on my membership site. So if that's something that you want to see, feel free to look into becoming a member. I'll have the details for that in the description of this video. Okay, but to summarize what we just went over here, the formulas for curvature are as follows. For a smooth curve given by a vector function r of t, the curvature at t can be found using either of these formulas. This one will be used most commonly. The curvature k is equal to the magnitude of the derivative of the unit tangent vector in terms of t, divided by the magnitude of the derivative of the vector function r of t. Or if you have a vector function with polynomial components or simple algebraic components, then you can find the curvature k by taking the magnitude of the cross product between the first and second derivatives of the vector function and dividing it by the magnitude of the first derivative of the vector function cubed. And by the way, in case you're wondering, the reasoning behind this formula being useful for polynomial components is because the cross product works nicely for those components, okay? That's not going to be the case if you have trig functions or exponential functions, or really anything that might involve a product rule. When taking the first or second derivatives, the cross product then gets very messy, so you would not want to use this formula. Okay, so the formula we looked at earlier was just the definition of curvature. You really only use that if you were already working with a vector function in terms of the arc length parameter, while these formulas here are more useful for finding curvature without the need to reparameterize. Okay, now I'm going to feel like a car salesman here, because wait, there's more. There's actually yet another way to calculate curvature, specifically a way that is helpful when you are given a plane curve represented by a function y equals f of x. And I am going to show you how we get to this formula because it involves a process known as vector encapsulation. And this is something that you might use from time to time in Calculus 3. And so here's what we're working with. We're going to find a formula for calculating curvature when we're given a plane curve represented by y equals f of x. Okay, and we're going to use this formula to help us find this other formula. So in order to make use of it, we have to rewrite this function as a vector function. So what we do is we encapsulate or enclose the function in a vector. We're going to let x equal t, and so by doing that, we can create a vector function r of t whose components are t, because x equals t, that's what we're saying it's equal to, and then y would be f of x, but x is t, so y would be f of t, and then there is no z component because we're working in 2 dimensions for a plane curve, so the z component is 0. All right, and so then if we're going to use this formula up here, we need to find the first and second derivatives of this vector function. So starting with the first derivative, r prime of t would be equal to a vector with components of 1, f prime of t, and 0. Right? The derivative of t is 1, the derivative of f of t is f prime of t, and 0 just stays as 0. And then for the second derivative, we have r double prime of t, and that will be equal to a vector with components of 0, f double prime of t, and 0. Okay, the derivative of 1, a constant, is equal to 0. F prime of t just becomes f double prime of t, and 0 is still 0. Now, using these two vectors, let's take their cross product. It should be pretty quick because we have a lot of zeros in our components. So we're going to take r prime of t and cross it with r double prime of t. And remember how to set up a cross product. You're going to have I, j, and k. We're essentially setting up a 3 by 3 matrix. The second row will have the components of r prime of t, and the bottom row will have the components of r double prime of t. So we have 1, f prime of t, and 0, and then 0, f double prime of t, and 0 again. All right, now doing the cross product here, we start by crossing out the I column, and then calculating a 2 by 2 determinant. But notice that f prime of t times 0 is 0, and then you'd be subtracting 0 times f double prime of t, which is also 0, so the whole x component is 0. You have 0i, and then you're subtracting the j term. So if we cross out the j column, you'll have 1 times 0 minus 0 times 0 for that determinant, which is also 0. So you have 0j plus the k term. So we'll cross out the k column, and then calculating a 2 by 2 determinant, you get 1 times f double prime of t minus f prime of t times 0, which is 0. So you'll just have f double prime of t. All right, so we get f double prime of t times k, and so that by itself is actually the cross product of these two vectors. Since the other two components are 0, we can just write it as f double prime of t times k. Now to actually calculate the curvature, we do need both the magnitude of that vector and the magnitude of r prime of t. All right, now starting with the magnitude of the cross product, it's just one term. So to calculate the magnitude, you take the square root of the sum of the components squared. But since there's only one component, you're only squaring one component, and then you're immediately taking the square root. All right, so the magnitude of r prime of t cross r double prime of t would just be equal to the square root of f double prime of t squared, which results in f double prime of t. So in the numerator, you just have the second derivative of your function f of x, which is what y is equal to. Now for the denominator, we need to take the square root of the sum of the components squared for r prime of t. So let's do that. The magnitude of r prime of t is equal to the square root of 1 squared plus f prime of t squared. Okay, you could add on 0 squared, but that doesn't really do anything, so I'm not even going to bother to write it. But then simplifying, the only thing that changes here is that this 1 squared would just be 1, and so I could rewrite that right in here and put in a 1, and that's it. We can't really simplify this any further. So that would be the magnitude of the derivative of the vector function. So this is what would go in the denominator here, and we would be cubing. Okay, so altogether, this is what we get. The curvature k will be equal to the magnitude of the cross product of the first and second derivatives, which we found was f double prime of t. But remember, curvature is a non-negative scalar value. It's always going to be positive. So we want to take the absolute value of that function to ensure that we just get a magnitude and no sign attached to the value. So we'll have the absolute value of f double prime of t, and then we are dividing by the magnitude of the derivative of the vector function cubed. And so you could write it in as a square root. What I'm actually going to do is rewrite it as this quantity to the 1/2 power, because then you'd have that 1/2 power being raised to the third power, so you can multiply those exponents and just have the 3/2 power. All right, so you just have 1 plus f prime of t squared to the power of 3/2. Okay, once again, we have the square root of that quantity. I'm just rewriting it as the 1/2 power, and so that whole thing would be raised to the third power, so multiplying the exponents gives you 3/2. All right, and that's it. This is the formula for calculating the curvature of a plane curve represented by a function. Now, of course, both of those t's would probably be in terms of x. That's fine. You could replace those t's back with x since that's what we let it equal to. But really, an easier way to write this formula is that the curvature k is equal to the absolute value of y double prime, or the second derivative of y. That's the same as f double prime of x or of t, and that would be divided by 1 plus y prime squared, all to the power of 3/2. All right, so the first derivative of f of x or f of t is the same as y prime, or the first derivative of y. Okay, so to summarize, the final formula for curvature, and I promise this is the last one this time, this formula is for calculating the curvature of a plane curve. So for the graph given by y equals f of x, the curvature at a point x comma y is represented by this formula. The curvature k is equal to the magnitude of y double prime divided by the quantity 1 plus y prime squared to the power of 3/2. And sometimes you will see this formula referred to as curvature in rectangular coordinates, okay? Because this would be in terms of x and y, as opposed to that parameter t or the arc length parameter s. None of those parameters are present here. We're just working in terms of x and y, which are the rectangular coordinates. Okay, and so that's a wrap. We have now looked at all the different formulas for calculating curvature, and so now we can finally take a look at some examples. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. For our first example, we want to find the curvature of the circle with radius r represented by the vector function r of t is equal to r times cosine t times I plus r times sine t times j. Okay, so we have a simple two-dimensional vector function here. We just have an x and y component, and even though we're told that it represents a circle, hopefully by this point you do recognize that that would represent a circle. When you just have cosine and sine as your two components, and they're both being multiplied by the same constant value, in this case we're just representing it with r, that is a circle. Okay, so if we want to calculate the curvature here, we have to decide on what formula we're going to use, and that might seem overwhelming at first because we just looked at 4 different formulas for curvature, but all of them have specific uses, and usually they won't all apply at the same time. All right, so if you take a look here, we're not working in terms of an arc length parameter s, so we're not going to use the definition of curvature, and we also are not working in terms of x and y, right? We're not given a function y equals f of x, so we're not going to use that last formula we just found. And furthermore, the components of our vector are not polynomial expressions. They're not terms like t squared or t cubed or t to the fourth power or anything like that. We have trig functions here. So we're not going to use that formula that involves a cross product of the first and second derivatives of the vector function. We're not going to use that here. Instead, the only formula that makes sense to use is the formula for calculating curvature in terms of t that involves the derivative of the unit tangent vector and the derivative of the vector function. All right, that formula looks like this. K is equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector function. Okay, so let's get started here. We need to find the derivative of our vector function, so let's do that. R prime of t will be equal to the derivative of these two components, and the derivative of cosine is a negative sign, so we'll have negative r times sine t, and that's multiplied by I, and then the derivative of sine is cosine, so we'll have plus r cosine t times j. Okay, and now we need to take the magnitude of this vector. So we'll have the magnitude of r prime of t is equal to the square root of the sum of these components squared. And I'm just going to square them right away. Negative r times sine t squared will give you r squared times sine squared t. So we have r squared times sine squared t plus this component squared, which will be r squared plus cosine squared t. Okay, so this is what we get underneath that square root. And then something really nice is going to happen here. We can pull out a common factor of r squared, and what you'll be left with is sine squared t plus cosine squared t. And we know from the Pythagorean identity for sine and cosine that that is equal to 1. All right, so what we get here is the square root of r squared times sine squared t plus cosine squared t. That is equal to 1, so you just get the square root of r squared, which is r. All right, so the magnitude of the derivative of the vector function is just the radius r. Okay, so that's what's going to go in the denominator here, but we still need to find the magnitude of the derivative of the unit tangent vector. So how do we find the unit tangent vector? Well, we have to remember back to a previous lesson in Calculus 3. We said that the unit tangent vector, capital T of t, is equal to the derivative of the vector function divided by its magnitude. Okay, because r prime of t represents a tangent vector, but then dividing it by its magnitude ensures that its magnitude is 1, so it will then be the unit tangent vector. So we just want to take the derivative of our vector function and divide it by its magnitude. And thankfully, that's not going to be too difficult here. This will be equal to 1 divided by r, that's just 1 divided by the magnitude, multiplied by the derivative of our vector function. So we have negative r times sine t times I plus r times cosine t times j. And then if you divide both of those terms by r, the r's all cancel out, right? This r will cancel out with this r and this r. So you're left with negative sine t times I plus cosine t j. That is the unit tangent vector. But now we have to take the derivative of that, okay? Don't take the magnitude of this yet. We need the magnitude of the derivative of the unit tangent vector. So let's take the derivative. Capital T prime of t will be equal to the vector whose components are the derivative of these components. And the derivative of sine is cosine. So we get negative cosine t times I. And then you will have the derivative of cosine, which is the negative sine. So you get minus sine t times j. All right, so that's the derivative of the unit tangent vector. Now we need to calculate its magnitude. So we will take the square root of the sum of the components squared, and that will give us the square root of negative cosine t squared. That negative will go away when you square it, and the same thing for negative sine t when you square that. So you'll just get cosine squared t plus sine squared t. And once again, we can just use the Pythagorean identity for sine and cosine. Cosine squared t plus sine squared t is 1, so we get the square root of 1, which is equal to 1. All right, so that's pretty nice. 1 is the magnitude of the derivative of the unit tangent vector. So the curvature k is equal to that 1 divided by the magnitude of the derivative of our vector function, which was r. So we have 1 divided by r, and that's it. That right there is the curvature of a circle with a radius of r. So whatever that radius is, if it's 2 or if it's 3, you can plug that right in here and find the measurement of the curvature. And this won't always be the case, but notice here that the curvature is constant. There are no values of t in this expression, and this would represent the curvature of the entire circle. So what this tells us is that circles have a constant curvature. And that should make sense. If you picture a circle, you will keep the same curvature all the way around a circle. You don't start bending sharper or less sharp at any point throughout the circle, so it does make sense that the curvature is constant. All right, and furthermore, this also makes sense because the bigger the radius, the less curvature there will be, right? As this r gets bigger, the curvature becomes smaller because you're dividing 1 by a bigger and bigger number. Okay, because if you looked at two circles, one like this and one like this circle has a bigger radius, and so the curvature is not as sharp because you have to make a bigger circle, whereas with this smaller circle, the radius is smaller, and so you have to curve more sharply to complete that circle, to draw that curve. Okay, so this formula does make sense. The bigger the radius, the smaller the curvature for a circle. All right, and be sure to make a note of this formula for the curvature of a circle. We will come back to this in a future lesson of Calculus 3. Okay, now before we end this lesson, I do want to take a look at one more example. Here we want to find the curvature of the plane curve represented by y equals x cubed plus 1. All right, so hopefully when you see this function, some bells are going off in your head, like, oh, I know what formula to use for that, because we have a formula for curvature that is useful specifically for plane curves given by a function y equals f of x. That's exactly what we have right here. Okay, remember that that formula is that k, the curvature, is equal to the magnitude of the second derivative of the function, or the second derivative of y double prime, and you're dividing by 1 plus the first derivative, y prime, squared, and all of that is to the 3/2 power. Okay, so we can set this up pretty quickly. We just have to take the first and second derivatives of this equation for y. So for the first derivative, y prime, that will be equal to 3x squared, right? We're just using the power rule for derivatives here. And then, of course, the derivative of 1 is 0. And then the second derivative, y double prime, is equal to 6x. We're just using the power rule for derivatives again. 2 times 3 is 6. Subtract 1 from the exponent, and you have x to the first power. Now, putting these two functions in their respective places in this formula, we find that the curvature, k, is equal to the absolute value of 6x divided by 1 plus y prime squared. So we'll have 3x squared squared. So we'll put that in parentheses here. We have 3x squared, and then that is all raised to the power of 3/2. And then simplifying, we do need to keep the absolute value bars around x because that could be a negative value. We're not told that x is restricted to be only positive, so you want to keep those absolute value bars there. We'll have 6 times the absolute value of x. You can pull out the 6 because 6 is always positive, but then you want to divide by 1 plus 9x to the power of 4 to the 3/2 power, right? 3 squared is 9, x squared is x to the 4th power, and so there you have it. That right there represents the curvature of this plane curve. If you want to know the specific curvature at a point given by an x coordinate and a y coordinate, you can just plug in the value of x into this formula and you will get the curvature. Okay, and then a little footnote here. If you wanted to, you could actually find the maximum curvature on this plane curve by taking the derivative of this expression and setting it equal to 0. and then you would just follow the process of finding a maximum or minimum value from calculus 1. So just keep that in mind. You could be asked to find the maximum curvature on a curve. If you have to do that, work with that equation you found for the curvature k, take its derivative, set it equal to 0, and find the critical values to then test them and see if they are a relative min or relative max. And feel free to go back to my Calculus 1 series if you need a refresher on that process. Okay, and so with that, this was the last example for this lesson video, but if you do want to get some more practice using all of the different formulas for curvature that we went over in this video, feel free to check out my examples video for this topic. I'll have that linked here on the screen. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.